think that fits very nicely. Do you?
Yeah, it should be
there. Exactly. I put it. Excellent. Thank you.
All right. So I'd like to thank the organizers for inviting me to give this talk. So I'm going to talk quickly today about twisty observables for deeply virtual exclusive reactions. I'm going to go ahead and kind of jump through more of the introductory slides because I don't have that much time. But we all know that orbital angular momentum is important that we need to find and study. So how do we see orbital angular momentum of the partons? Well, what we can do is we can define an average using a Wigner function, which can be then parameterized in terms of the GTMD F14. So this is kind of the name of the game here for orbital angular momentum. And now it's a question of, is it observable or not? So there's no formalism or complete framework yet for GTMD observables, but from what I was going to talk about tomorrow is this summary here, in which you can relate the KT squared moment of F14, which is the average orbital angular momentum. The first derivative of it can be described in terms of twist 2 GPDs and a twist 3 GPD E2T tilde. And so now the question is, can we disentangle the twist 3 GPDs from the DVCS data?
Yeah, but as I understood from Abad's work, so this F14 is derived for the straight twist on 9.
Right.
So it's not, it's different from the canonical observable that's shown in the previous slide. So,
Okay, this is from the
it's not,
straight question.
it's not the light front gauge link, it's a straight gauge link, but still a canonical would be Fock-Schwinger gauge, actually.
so
It's the canonical Fock-Schwinger gauge, not the canonical in the light front gauge.
So it's different.
It's different from the total covariant derivative. If you look at the normal, if you integrate over French momentum, you get a local operator. But here you still have the non-local operator, so it remains canonical, but different from the light front one. Okay, but we can discuss this afternoon.
Okay, yeah, this is from this afternoon.
Yeah. All right. So, so the question remains: can we disentangle the twisted GPDs from data? So we're going to talk about a couple processes today. I'm going to talk about DDCS, in which when you define your hadronic tensor, you can kind of isolate the sectors of the hadronic tensor you can find from DVCS. So you can see the twist 2 sector here, and only parts of the twist 3 here. These are not accessible for DVCS. So here's just a quick, this is your leptonic plane. This is your hadronic plane. You have the quark moving along the negative z axis, the proton moving along the positive z, and you emit a real photon and a proton with a different momentum. So this is the total cross-section for DVCS, written in terms like something similar as you do for TMDs. And you can separate it out into various components of polarization. So you have completely unpolarized. The first view here is like the beam, and the second one's the target. So you have completely unpolarized observables here. You have your longitudinally polarized beam, unpolarized target. The opposite, unpolarized beam, longitudinally polarized target. You have your completely longitudinal observables, and then you have your transverse polarized target observables. So using this, we can sort of unpack what we want to look at. So you can what we can see right away is actually that through various through parity, we can actually eliminate 5 of these observables because they are just 0 identically. And then what you can do is you can look at, okay, you can isolate, these are the twist 2 components here, and then you can similarly do the same game for twist 3 and also for twist 4. So now, how do we go about defining or calculating these observables? Well, first we take our normal handbag diagram and we define the photon, proton. These are the photon. These are the proton helicities and the photon helicities, and we define these amplitudes as a hard scattering here, multiplied by a matrix element A, which has the G.
So the reference is the paper with Osvaldo, right?
Yeah.
Okay.
Yeah.
That's with the Said. But it's okay. It's okay.
Yeah.
There should be Osvaldo in there.
Okay.
Osvaldo Gonzalez. Okay.
Gotcha.
But anyway, yeah.
Yes.
That's okay. That is.
So, of course, we're doing this simply at tree level, so we can extract this G as just taking this as a quark, anti-quark, and separating these out. So we have this quark helicity and photon helicity amplitude, and you can see that similar to what we did with the hadronic tensor, we have mu and nu are both transverse. This corresponds to twist 2. And then when we have the gamma star, and when it's longitudinally polarized, we can access the twist 3. So once we calculate these, you can see that they have a certain phase structure that you can then check against the phase structure that you develop, because this is kind of like a definition of an amplitude according to Jacob and Wick, the old paper. And so what you can do is you can check and make sure that these obey certain helicity amplitude rules, and from here you can isolate the angular dependence that you saw emerging in your cross-section. So you get something that looks similar to this, and same thing for the transverse structure functions. So now you can take your cross-section and you can use these helicity amplitudes and the angular dependence to then kind of isolate what structure functions are you looking at. So this is kind of like the twist 3, one of the twist 3 pieces that enters into your cross-section. And when you do the summation and you use your amplitude rules, what you end up getting is you end up isolating with the cos phi dependences and sine phi dependences, the twist 3 terms, the 0, 1, and 0, minus 1. And then let's say you want to look at the unpolarized cross-section, which you would take the lepton helicity to be plus and the incoming proton helicity to be plus, and you add it to the minus minus. And so you get like FUU cos phi is something like this by parity. And then you also see by parity that FUU sine phi, which is this term, ends up actually disappearing. So now we have these observables in terms of the GBDs, because we've inserted the amplitudes, which are in terms of GBDs. So these are some of the twist 2 observables, not all of them, but you have the unpolarized observable here, and then you have your longitudinally polarized observable here, and then here is the unpolarized beam on a transversely polarized target in terms of your GBD. So you can see you can access various regions because for DVCS you can only access the twist 2 and twist 3 GBDs, but of course the answer is Compton form factors. So you have 4 GBDs at twist 2, and you have 8 at twist 3, and then you multiply by 2, so you get 24 in total. So we're hoping, or it's ideal that you'd be able to access all 24 of these observables. So then you can imagine these in terms of their helicity structure. So H is given by this unpolarized. So this is just a way to kind of wrap your mind around what you're looking at in terms of the GBDs. And they also come with specific phases. So then you can do the same game for twist 3 observables. So these are just a couple of them. And what you can see is that they come in linear combinations of the vector and axial vector GBDs. So this is kind of the question is, can you So we're looking specifically for E2T tilde. I mean, obviously the rest of these have more specific physical meanings, but E2T tilde is the one we important for orbital angular momentum. And now, but you see that it's it's tangled up with E2T tilde prime, and you see this actually ends up happening for all of your DVCS observables. So it's can you find a way to take what you have and disentangle it? But what are these linear combinations of GPDs? Well, in order to kind of think about that, you would need to kind of describe good and bad components. So you can take your projection operators, you project out a good component of your side and your bad component. And so your good component is just basically defined in terms of your bad components. So your bad component is in terms of your perpendicular gluon fields, and your good components is kind of it's dependent on your independent variables here. So so a quick picture of what this looks like, or how you would do the calculation, at least in terms of the amplitudes, is let's say you want to look at the operator gamma 1. Well, you can write this out, and you can expand your good and bad components psi in terms of a basis here, and you can then see kind of what you're looking at in terms of good and bad components here. So these are kind of the when you do the inverse. So you look at linear combinations of these correlators, and you look at what GPDs you're accessing. Each of these kind of has like a physical meaning here. So this is kind of the idea behind OAM, and similarly, when you look at the axial vector, you get the spin orbit coupling. But I mean, the rest of these have physical meaning. It's just figuring out and playing the game with the helicity amplitudes on what you're looking at. So you can also access twist4 observables, but as you can see, these are not truly these are not in terms of the twist4 GPDs, because we can't access the twist4 GPDs. We would need 2 longitudinally polarized photons, which is not DVCS. So, but the twist4 observables that you're seeing here are kinematic twist4, so you've got an extra suppression of P plus from twist3. And these are given in terms of, similarly with twist2, as you saw, these were mod squares of your GPDs. You get similar mod squares of your twist3 GPDs. So there's additional observables that come into play when you're dealing with DVCS, because DVCS also has a background process, beta Heiler. So when you're looking at your total cross-section, you're not just looking at DVCS, you're looking at DVCS squared, beta Heiler squared, and then you've got this interference term. So these are originate new observables that you can calculate also for twist2 and twist3. But so these are important, because I think these are the a helpful tool in isolating more of your observables that you need. So the next process that I'm going to talk about is actually TCS. TCS, what you do is you have a timeline photon. So now you're looking at a different sector of the hadronic tensor. And what you see just right off the bat is that your operators that you were originally looking at in DVCS, the axial vector sector just switches sign. So that's kind of an interesting thing to think about in terms of when we were looking at our observables at twist3. We had linear combinations that were like E2T tilde plus E2T tilde prime, and now we want to look at maybe this sign change is going to affect in terms of our TCS observables. So I calculated quickly, like, so this is my DVCS, this is what you've already seen, and this is just something that has, this is one of the terms, that has E2T tilde in it. And now when I look at TCS, you can see that all of the axial vector observable, all the axial vector Compton form factors actually change sign. So it's not just DVCS alone that we need to look at in order to isolate E2T tilde. It's actually, if you look at DVCS and TCS and you sum these, you can isolate independently the vector versus the axial vector sector. Sum or subtract.
Can I ask a naive question?
Sure.
So let's assume I measure surfaces of DVCS which are sensitive to this twist 3 GPD. And then I do the same for TCS. But then I still don't measure the full Compton form factor. I measure only a small area. And what the puzzle for me is, so that is an incredible, nice decomposition and a very hard calculation. I appreciate all of this. But the thing is, how do I, as an experimentalist, how can I help to kind of get to these quantities? Because they are not directly measurable. I measure an observable like a cross-section or an asymmetry in some phases. And so how much of the phase space for these guys do I constrain?
Well,
or should we wait until this after?
You go to the observables? Do you have some of the observables? Do you have the asymmetries?
No, I don't have the asymmetries. But that's something that we're actually looking at is writing these in terms of asymmetries.
Okay.
Yeah. It's but
no, okay.
For the asymmetries, it takes a little bit more because you're doing
2 hours.
Yeah. Because
no, it's okay.
Yeah, because then you're trying to take these, sum them, and put them into over top of your unpolarized cross section. So, but yeah, that's not been done yet. But
That's fine. Yeah. That's a fine answer.
Yeah. So then, kind of wrapping up, it would be I think what would be really interesting to look at would actually be the process double DVCS, because you can isolate. Well, you have access to full hadronic tensor. You don't have to look at just one process versus another process. Here you have you're actually able to get to both sectors that you want to use, and so maybe through double DVCS you can access OAM through just a singular process instead of needing 2 processes. And so maybe when to develop a formalism for double DVCS would actually be useful. And so that brings me to actually my end. So we see basically that DVCS alone cannot isolate the twist 3 GPD connected to it. So you can't use just purely DVCS to access E2T tilde. But along with DVCS, you also get extra observables through beta Heitler interference that could possibly be usable. And when you combine the observables from DVCS and TCS, you can actually isolate the E2T tilde. So that's something that we are actually exploring further. And lastly, there's a lot more work to do because it'd be interesting to look at the formalism of double DVCS or possibly processes and develop the formalisms for processes to measure GQBs directly. So thank you.
Thank you very much. So other questions?
So what's double DVCS?
So DVCS, you would just have this.
Yes.
There, so double DVCS is that you have a virtual photon on both sides.
Using the virtual photon which plays into
Do you have any idea what the cross section of that is like? No.
It's going to be tiny, of course.
It's
like one is triangle. Okay, so it's not quite symmetric.
Yeah.
So the cross section is indeed very small. And my understanding is at JLab they have done an enormous amount of work to look to double DVCS. And even in fixed target, actually it's challenging to get the luminosity to measure this. I think it is pretty safe to say that in a collider, it's very good. If not, I don't want to say, who told me this? You should never say it's undoable, but it's close to, let's say.
It's like the ultimate marriage between DIS and Raylan.
Yes, however, yes, but it is interesting.
Yeah,
Exactly. That's why I'm saying it's not.
Yeah, but so the practical way, he showed the practical way and the ideal way. The practical way is you compare, you not only look at DVCS, you also have DCS.
Exactly.
But that is two different experiments. Okay, so all kinds of issues about universality come up.
But even with EIC,
Yes.
huge luminosity.
So-
I mean, so I'm thinking
So
about
at
factor
chain
of 10,000
now at
spread.
chain they talk about luminosities of 10 to the 38 to measure double DVCS.
Say in JLab,
10,
the 10 to
10, so there have been nice studies by JLab
and they said
for
that-
double DVCS, and the luminosity numbers they talk about is 10 to the 36, 10 to the 38. That is not doable in a collider. You just cannot fit so many protons and electrons in a bunch. They don't, they happen saturation and they explode. So it just doesn't work.
Although the cross section will rise very strongly at colliders, but it's going
There was, we had a workshop at JLab where Simonetta was as well, where some of this was presented, and even it's true the cross section, but still, then you have divide by the unpolar, and the asymmetries get tiny and so on. It's really difficult.
Yeah. So, however, so the people that are doing this are Alexander Kamson and others at Jefferson Lab. I am not sure that they have entirely given up on it yet, but yeah. So okay. So what I personally think is that so there's no formal. There's been no formalism really, and so the way they've been doing their estimates is not entirely, precise. However, so to develop the formalism is a lot of effort, and so at the same time, this is where I was like, oh, should we do it? And then this is like, not measurable, but at the same time, you need a little bit of a better stab at the formalism. So that's why we've been looking at it.
So didn't Peter Kroll work on this, or was that Peter Kroll?
No,
No?
Peter Kroll, not that I know. Peter Kroll, I don't know. I mean, not that I recall.
I saw
The theorist, there is not. So the people that did this is Kamson, and then it's Guichon. Guichon, sorry, Michel Guidal. Yeah. Michel Guidal and Marie Boyle. So they've been looking at it, and Guidal has also part of the formalism because it's with that. So yeah, that's at the connection with Kroll. So probably yes.
That's right. Okay.
More questions?
Exactly.
So there are good indications that twist 3 GPDs are discontinuous, as Matthias discussed. And this discontinuity may endanger the factorization. It turns out that for DVCS, the linear combination are those that are safe.
No.
When you go to TCS, you observe that the orthogonal combination is the one that is safe for that process.
No, so we haven't done any of the model calculations for those linear combinations.
And that would be consistency check, sanity check. Okay, thank you.
That delta dependence is a model calculation. That's our point of view. This is before the model.
Yeah, okay.
So that there is a delta, and that creates this continuity. It's within a model. So this is for experiment to verify.
Yes, you have to make sure that factorization, which is not proven, is not broken by discontinuities in your functions. So you have to make sure that the evolution, for example, the Tansel check, which is probably not too bad approximation,
Right.
is consistent with the factorization hypothesis.
Right. So
So it's probably correct that it's good to have
So the
this.
studies are very similar to the PDFs. You
We don't have discontinuity.
So you can think of it with the origin at x equals 0. It's very similar to the redshift.
Yeah. For DVCS,
So
you have to be careful. So it's probably correct. It's good to check. That's what it.
So the discontinuity is not part of the. So this precedes this formalism precedes that as a model dependent statement. There is the same statement, in other words, that's saying that little g2, okay, the little g2 has a delta at x equals 0. Might have a delta at x equals 0. But we're saying it might have a delta at x equals 0 within a class of models. Okay. So okay. So all right. So
Well,
yes, so one has to
the
prove
core-
factorization from this.
Okay, the core target model is still a model. It's from that you can develop these discontinuities, but there's the same object that enters essentially evolution, so which means that big lab evolution will also be consistent with if there are discontinuities in the GPT. So it has.
Yes, but it's a model. It's a model.
Yeah, no, evolution is not a model.
Evolution is not a model, but that's the core target. So the core target model generates the same, it's nothing to do with evolution. So
Okay. Are there more questions for Brendan? If not, I suggest we thank Brendan, actually. And then we meet again at 2:30. I think we have this room today, so we can meet here. If not, I think so, from what I saw. If not, we go next door. It's an easy thing to do.